Welcome back to Algorithms. Today we'll be talking about some divide and conquer methodologies for sorting, the first of which is merge sort. So we talked about merge sort last time, and the basic philosophy of merge sort goes like this. One, we take an array, an unsorted array, and we cut it in half. So we cut array in half. Okay? We'll call this the splitting operation. And so our splitting time, the amount of time it takes to split an array, we determined is constant time, because all we're doing is cutting the thing in half. It doesn't matter how long it is, right? Finding the middle index is not a difficult thing to do. Okay, so second, what we do is we take both halves and we say, hey, merge sort these, right? So we recurse on both halves, right? So now we recurse on each half. All right, what's this mean? We trust that the merge sort algorithm will be able to handle these things, right? We say, I don't know what to do with these. These aren't sorted. I can't do anything with them. You go sort it, self on the call stack. Okay, so we recurse on each half, and so this gives us a term in our recurrence relation that looks like this. Right? We have two recursive calls, because there's two halves, and each of the arrays, the array that each half is operating on, is half the size of our input array. Right? So we have this 2 times t of n over 2. All right, so the sorting works, right? But we'll just trust the sorting to work, and we'll see exactly why that is in a second here, but the sorting works. So after that recursion is done, right, those two instances of merge sort give us back two sorted arrays. Right, so now the halves of our original array have been sorted, and so now what we have to do is combine those back together into a sorted array. And so after the recursion is done, we recombine those sorted arrays into one big sorted array. So we'll combine, or the term is merge, right? We'll merge sorted halves into one sorted array. And we'll call the time it takes to do that C of n. And we'll say, and the question for today is, what is the complexity of C of n, right? What does it actually take to do this? Because the complexity of C of n will govern how fast this algorithm is overall. So last time what we showed is that if C of n is linear, then we can use the master theorem to show that merge sort is n log n. So if C of n can be done, right, if we can combine two sorted arrays into a sorted array in linear time, then what do we have? Well, we have that merge sort, the overall T of n of merge sort is big theta of n log n, which is a considerable improvement upon our elementary sorting algorithms. So let's think about what this would take, right? Can we do this? And before I do that, I want to give you the full kind of pseudocode for merge sort. It's not very complicated, but at least it may be helpful to see. So let me do this. Let me write the algorithm, and I'll call it merge sort. And it'll use this merge function as a subroutine, and then we'll go analyze the merge function. So our algorithm merge sort looks like this. So A takes an array of size n, and then what does it do? Well, it establishes a base case. So if n is equal to 1, then we just return the array. But if n is greater than 1, then we call the merge function on a merge sorted version of the two halves of the array. And so the way to do this is like this. So we return merge, and so we'll talk about merge in a minute, but we'll just use it as a subroutine here. We'll return merge of merge sort of the first half of the array, right? So this is A starting at 0, going up to n over 2 floor minus 1. Minus 1. Right? So we're going to execute merge sort on the first half of the array. We're going to execute merge sort on the second half of the array. And now what is this? This is n over 2 floor, all the way up to n minus 1. And then we'll pass those two, whatever merge sort gives us back, we'll pass those two as arguments or as inputs to merge, to the merge function, which we'll talk about in a minute. So that's if the array is not a trivial array, right? If it has more than one element, this is what we do. Otherwise, what do? We just return A, right? If there's only one element in A, it is sorted trivially, and so we just pass it back up. So else we return A. Okay, so what's the goal of merge sort? The goal of merge sort is to take an unsorted array and then return a sorted array. Okay, so as long as this line works, then merge sort works. Right? So as long as we can trust that whatever merge sort gives us back is sorted, and then we can trust that the merge function creates a sorted array, then we're done. Okay? So let's think about what merge might look like, and I'll write some code, some pseudocode, and then we'll think about how to analyze the merge function. Right? What is this actual merge function trying to do?